distinguished guests, staff and students, ladies and gentlemen. On behalf of the Faculty of Science, Chiang University, may I wish you all a very warm welcome to this lecture, the third in a series of Nobel Laureate Science Lecture. Hosted through the International Peace Foundation, this series of lectures is aimed at bringing some of the world's leading scientists to countries such as Thailand, in which science and technology have such important roles to play in the country's social and economic development. The speaker in today's lecture is Professor Nicolaas Bloembergen of Harvard University and University of Arizona. Professor Bloembergen received the Nobel Prize for Physics in 1981. Now, may I introduce the chairman of today's session, Professor Nicolaas of Department of Physics, Chiang Mai University. Professor Nicolaas is Thailand's leading scientist with many outstanding research awards from various funding agencies. He is the director of the Fast Neutron Research Facilities and has recently been elected the president of the Thai Institute of Physics. Now, may I kindly call upon Professor Nicolaas to formally conduct this afternoon's lecture. Thank you.
Good afternoon, ladies and gentlemen. I think it's very warm today, and especially warm when we have visited us today a very distinguished physicist and teacher, Professor Nicolaas Bloembergen. And today I would like to introduce Professor Bloembergen, his remarkable career in research and teaching. But first, I would like to call upon Dr. Nicolaas, the President of Chiang Mai University, to formally give a speech, welcoming speech, and to start this reading this afternoon. Please.
Professor Bloembergen, Mr. Janis Nicolaas, Director of Events Corporation of International Peace Foundation, Dean Professor Tontam, and Professor Thirapat Beretom, distinguished guests, ladies and gentlemen. One of the privileges that bestowed upon me as President of Chiang Mai University is the opportunity to preside over occasions such as this. Professor Bloembergen, it is indeed an honor for me to welcome you to our university on this most auspicious occasion. Professor Nicolaas Bloembergen is with us today under the auspices of the Nobel Prize Laureate in Science Lecture Series, a program which will provide our staff and students with a unique opportunity of coming face to face with the most distinguished scientists. A once in a lifetime opportunity that I am sure will be a great source of inspiration. I would like to take this opportunity to express our gratitude to the International Peace Foundation, without whose support today's lecture would not be possible. Also to thank the Dean and his colleagues in the Faculty of Science for the time and energy they have contributed to organizing and hosting this event. Professor Bloembergen, please accept our most sincere thanks and appreciation for honoring our university with your presence. And I trust that memories you take with you of our university and our city will hasten your return in the not too distant future. Thank you.
Thank you very much, Professor Nicolaas, President of Chiang University. Next, I would like to ask Mr. Nicolaas, on behalf of the International Peace Foundation, to introduce us about this series of lectures.
Thank you. I'm going to say a few words on behalf of Bloembergen, Chairman of the International Peace Foundation, who unfortunately cannot be here today, but who expresses his best wishes to all of you. Ladies and gentlemen, dear friends, I have no concept for peace and no solution how to achieve peace, but I know the first step towards peace is dialogue, and the first step towards dialogue is respect. The International Peace Foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue where people meet who normally don't meet, so people from all different kinds of work, who speak the different languages, even if they use the same. As politicians speak another language than artists, and business and religious people another than scientists, it is seldom that they speak with each other or even work together. We live in a world where some people pretend to know the answer and solutions, how to solve problems, how to achieve peace, thought the quest for peace lies in the art to pose the right questions. Peace is a process, dialogue is a process. It is nothing which is achieved instantly. It needs time. This is why bridges is not organized as a single event and then everything is over again and forgotten, but it is organized as a series of events in which 24 Nobel laureates for peace, physics, chemistry, literature, medicine and academics build bridges with Thai leaders in all parts of society and with the general public. This is why we want to further encourage your input and support, and why we look forward to your questions and suggestions, your advice and guidance in this dialogue process towards peace. I thank the Chairman of the Thai Advisory Board for the event series Bridges, His Excellency Anand Panyanchun, President Professor Nipon Juvanon, Vice President Professor Tonan Anuman Rajaton, the Chiang Mai University, and all sponsors and partners for our fruitful cooperation, and especially Professor Nicolaas Bloembergen, who came to Thailand without any honorarium to support the events, and I now look forward for his keynote speech and his important contribution to build bridges. Thank you very much.
Thank you very much, Mr. Wang. Next, I would like to introduce Professor Bloembergen to our audience. There is a few pages, many pages of what has been written about Professor Bloembergen. I think today I would like to share with you some of his remarkable areas in teaching and research. If we remember, in 1981, the Nobel Prize in Physics was awarded to 3 physicists. Professor Nicolaas Bloembergen was awarded the Nobel Prize in Physics with Professor Arthur Chiang from Stanford University for their contribution to the development of laser spectroscopy. Also, the third person was Professor Kai Sigban from Uppsala University, whom we know quite well. And Professor Bloembergen was born on the 11th of March 1920 in the Netherlands. And this is a very special year indeed, as we know that the Queen of the Netherlands will pay a royal state visit to our kingdom next week to commemorate the 400 years of relationship between the two countries. Professor Bloembergen received his high school education at the Municipal Gymnasium in Utrecht. Now there is very special about this school that nearly all of the teachers has a PhD. Remember, this is a high school, all the teacher has a PhD. Our physics department is supposed to be the biggest physics department in the country, but not all our teachers have PhD. So he received his master's degree from the University of Utrecht, and at the same time he published his first paper in physics in 1940. Then in 1945, Professor Bloembergen came to Harvard University to start his PhD on nuclear magnetic resonance in solids, liquid, and gases. It is quite remarkable to us that his PhD thesis on nuclear magnetic relaxations was published. Some of this was published in the Physical Review journal, and was one of the few papers that has very, very high citation. After his PhD, which he submitted to the University of Leiden, he came to do his postdoctoral during the year 1948-1949 at the University of Leiden. Then in 1949, Professor Bloembergen started his research and teaching career at Harvard University in the United States. Of course, he has made a rapid advancement in his career, become a full professor of applied physics in 1957 and a full professor of physics in 1974. His research spanned a very large field. He did some work in nuclear physics also at the Harvard Cyclotron, and also on microwave spectroscopy before he started his work on the nuclear protocol interaction in alloys and imperfect ionic crystal. That was in 1950 and the 50s. And then in the 60s, when we were enjoying the Beatles and all that, Professor Bloembergen started what is known as the nonlinear optics, field of nonlinear optics, which is still a very popular and very, very interesting field nowadays, and enjoy more and more of its application. Especially we know that his interest in the interaction of picosecond and femtosecond laser pulse with condensed matter. The subject of femtosecond, which we share some interest here in Chiang Mai, where we start developing some femtosecond electron pulse from linear accelerator. Professor Bloembergen has received many honors and awards. I think we can fill up about 2 pages. But I would like to mention some very, very important awards. For example, the Oliver Buckley Prize that he received from the American Physical Society in 1958. The National Medal of Science presented of the President of the United States of America in 1974, the Medal of Honor from the IEEE in 1983, etc. He also has been a visiting professor in many places in the United States, in Europe, and in Asia. Also, to my delight that he was in 1991 the President of the American Physical Society. So welcome back to the Thai Institute of Physical. Welcome. And I think the least, most of all, he has been married to Mrs. Iveta Liriana since 1950, and both have one daughter and two sons. So today, I think it is our privilege indeed that we will be able to listen to a lecture by Professor Bloembergen on the utilization of laser, I believe, in optical science and technology. I think the exact title, official title is Science and Communication based on optical science and technology. So may I please invite Professor Bloembergen to
Thank you very much for the extensive introductions. I'm afraid that will take time away from my talk. The title of my talk is really Lasers in Peace and War. And I'd like to talk about the various applications of lasers, how it affects our society, societies in every country of the globe. And I begin by commenting on the word laser, which you undoubtedly have heard and read about before. But it really stands for light amplification by stimulated emission of radiation. So it has its roots in the English language. But the word laser is used in most other languages as well. And the first laser was built in 1960. And that was also the period of strong confrontations between the Soviet Union and the United States. But the Russian scientists also used the word laser. And even during those periods, there was a lot of communication between Soviet scientists and scientists in the United States and elsewhere. So in a way, the language of science is quite universal and transcends otherwise difficult boundaries. Now I'd like to begin with explaining to you what stimulated emission of radiation is. It's a little bit of physics before we start to show various applications of these light sources. May I have the first slide? Can somebody turn on the machine? What do I do here? I just look forward. All right, thank you. I get it. And is this a pointer? mean, I don't need it. Yeah, I understand that, but I don't need that. That's a microphone, right? I don't need that, but I do need a pointer. Light gets created by electrons which circle around in atoms or molecules. And all the light before there were lasers was emitted by a process called spontaneous emission. Spontaneous emission is when an electron falls from an orbit with higher energy to one with lower, and then the difference in energy is radiated as a light quantum or photon of energy h2. And here you see one with a larger energy difference, and that sends out light of a higher frequency or shorter wavelengths. That is spontaneous emission. Now, the next slide shows you two other processes. The most common one is absorption, and all materials in this room except the lamps which have spontaneous emission. All the other materials here, clothing, tables, and so absorb light. Curtains. And they absorb light because usually the electron is in an orbit of lower energy, and then it absorbs a light photon and the electron gets excited to that orbit. And you see, of course, that the light intensity decreases because you take photons out of the light. Now, stimulated emission, which was introduced by Einstein in 1917, is just the opposite of that. That initially the electron is assumed to be in the higher orbit. The light comes in, and then that electron gets stimulated to emit in exactly the same direction and to amplify the light wave. So rather than spontaneously emit in an arbitrary direction, it really adds to the light wave that stimulates that electron to lose its energy, and so that the light wave increases in intensity. And you see that in order for the stimulated emission to win out over the absorption, you have to have a material where electrons are more in the orbit with higher energy than in the orbit with lower energy. And that is never true for any material in thermal equilibrium. You have to do something special. You have to pump up the material to get more electrons in the state with higher energy. And that is done as follows. That here you have the lower energy state, and then you pump it up to a very high energy state. And then you get more electrons in this state than in this state, which was completely empty. So the electrons which were in the ground state get to this upper level, and then you have more in this upper level than in this intermediate level. And that's why you get laser output, amplification of light, that energy difference. And that is the physical idea to create a laser. And here you see a particular energy diagram. Of course, each substance has different energy levels, but these are the energy levels of chromium ions in ruby. And ruby was the first crystal that was made to lasers in 1960 by Main. And what you do is you shine in from a photographic flash tube from these levels in the ground state to the ruby absorbs blue and green light. That's why it has a red color to begin with. And then the electrons in these higher orbits drop down here, and you get more electrons in these fluorescent states than in the ground state. And that's why you get laser light out at 694 nanometers. That is red light. So the next slide shows you the difference between spontaneous emission and stimulated emission. In analogy with a crowd of people, that here talk in all directions, walk in all directions. That's the spontaneous random motion of people on the fairgrounds or in a big marketplace. And compare that to a military column where all the individuals walk in step and get reinforced by the marching music. And that is what happens in the laser. All photons go in the same direction at the same frequency. That's the difference between coherent light from stimulated emission versus random light from spontaneous emission. And here you see how that thing builds up. Suppose that this is the atoms in a ruby crystal, the chromium ions, and they are placed between two parallel mirrors. Initially, they have spontaneous emission in all directions, but then the light that gets normal to the mirrors gets reflected, and more photons get added to that dominant wave, and then finally you get an output from the ruby laser. And the light that is so amplified, and here is really the mechanism of the first laser, that had only these components. It had a ruby crystal, and these mirrors on the end faces that were made parallel, and this mirror is slightly transparent, and then you pump it up by means of a photographic xenon discharge flash tube. That pumped it up, and that is why you got the laser action. And this is another laser, helium-neon laser, also found in 1961, where you pump a gas with an electric discharge, a mixture of helium and neon gas. But the idea of stimulated emission is the same in most cases. Now, why are people so excited and why did lasers get so many applications? Because the light emitted by them has these characteristics. It's all at the same frequency, and I won't talk much about that, but scientifically that's very important. The frequency is very pure and can be defined to 14 or 15 decimal places. And future time standards will be based on the frequency or the wavelengths of lasers. And it has many scientific applications which we cannot go into today. What is important for us is the directionality, and of course this pointer is one example of the directionality of a laser beam. But we will see more important practical applications of that in a minute. And then also you get very high intensities because of the directionality you can focus that light to very small spots, and you can get spot sizes that are equal in linear dimension to the wavelengths of light. That is 1 micron, that is 1 millionth of a meter. Very small spots because of the high directionality that's possible. But if you don't focus them, but just send out the light of a laser from a telescope on Earth with 1 meter direction, then you see that this angle of spread, this delta theta, is 1 millionth, 10 to the power minus 6, because this is a micro and D is a meter. And if you point that telescope towards the moon, you only hit an area on the moon equal to a soccer field, to a football field, 100 meters wide, 100 by 100 meters. And the astronauts in the late 60s put up retro-reflecting prisms on the moon, and then a laser was shown by this telescope toward the moon and got reflected back. And people could measure the time it took for the light pulse to travel to the moon and back to the Earth. And they could measure that distance to a precision of a few centimeters. And you say, who cares whether it is exactly how many centimeters? But then somebody in Japan did the same thing using the same reflectors going back to Japan. And so he got the distance from that point in Japan to that reflector on the moon. And then by triangulation, you know exactly the distance between a point in the United States and a point in Japan. And you can still say, who cares how many centimeters that is. But then you repeat that a year later, and then that distance between the two continents has changed. And that is geophysically very important, that due to upwelling of material in the oceanic ridges, in the middle of the Pacific Ocean, middle of the Atlantic Ocean, the continents are spread apart further. And that is very important for the structure, the tectonic structure of the Earth. Well, that is one scientific application. Let's now go to Earth. In fact, because of the limit, you can focus the light of a laser on very small distance. You can go to 1 micron, but here I only go to 100 microns. So I don't push science at all. But you can concentrate light not only in space, but also in time. And you can easily make pulses as short as 10 to the minus 11 seconds. That was done early, in the mid-60s. Nowadays we can get pulses of 10 to the minus 14 seconds, 1,000 times shorter. I won't give that example, but I want to show you what happens. You take a millijoule of light, 1,000th of a joule. That's a very small amount of energy, because a 100-watt light bulb consumes 100 joules every second. That's what 100 watt means. 100 joules per second. So a millijoule is consumed by the 100-watt bulb in 100,000th of a second. Really a very small amount of energy. But when you concentrate that energy in space and in time, this little calculation shows that at that focal spot, you get an intensity of 10 to the 12 watts per square centimeter. Because your focal spot is 10 to the minus 4, the time it takes is 10 to the minus 11 seconds. So you have to divide those 2 powers of 10, and this is your answer. And 10 to the 12 watts is also called a terawatt. And it is equal to the total power generation of all electric power stations on Earth. And imagine all that power generated on Earth concentrated on 1 square centimeter. You guessed it, all hell breaks loose, and every material is very rapidly converted into a spark, a high temperature plasma. Evaporates immediately. So you keep applying these magnitudes due to concentration in space and time of the laser light. And here you see that near the equator where we are, if the sun stands in the zenith, it illuminates us with 0.14 watts per square centimeter. That is less than 2/10 of a watt per square centimeter. And that makes you feel uncomfortably hot. Now, at the surface of the sun, there's black body radiation of 6,000 degrees Celsius or centigrade, or Kelvin. And that corresponds to 10 kilowatts per square centimeter. But we are talking about terawatts. That is 8 orders of magnitude higher. And as I said, you can make the pulses shorter and you can focus them sharper, and we can get in the laboratory to 10 to the 20th watts per square centimeter. And that corresponds to conditions that exist in the interior of stars. That is black body radiation at 6 million degrees or more centigrade Kelvin. Now, this, of course, before that happens, you get all kinds of other phenomena, and these are the phenomena of nonlinear optics. That here is a crystal which is transparent. This happens to be potassium dihydrogen phosphate, and here comes the ruby laser pulse in, and it gets converted to ultraviolet light, which is the second harmonic generation of light. Just as in a string instrument, if you hit it too hard with your bow, or if you know organ pipe and you blow on it too hard, you get harmonic overtones. You get harmonics, multiples of the sound frequency. Here you get a multiple of the light frequency. And you convert 2 red photons into 1 ultraviolet photon. And that is a basic new phenomenon of nonlinear optics. And there are many other processes that occur at high intensities, even though they don't do damage because the crystal remains transparent for a while. This is the ruby laser pulse in 1961 that got focused by this lens into the air, and it created a spark because the intensity got so high that you ionize the air molecules, the oxygen and the nitrogen. And this happened to be done by Dr. Terboon, who then worked at the Ford Motor Company research laboratories in Dearborn, Michigan, and he called this the most expensive sparkler in automotive history. And of course, lasers have never been used as practical sparklers, but because there are simpler ways to make sparks in air or in gas mixtures. But it shows you the power of the laser. And in those early days, people didn't talk about watts per centimeter. They talked about the units of gillettes, because they used this ruby laser pulse to pierce through metal razor blades, Gillette blades. And here the scientists said, 5 Gillettes, very powerful ruby laser pulse. Well, of course, this was not lost on the military, and they immediately started talking about Star Wars ideas of having a block of light hitting in an intercontinental ballistic missile. And there was a weekly journal or a newspaper that showed this picture, and they called it the incredible laser. And it's still incredible, it still doesn't exist. This bad dream has not been realized. And it says here, this is from Professor Schafel, for credible lasers, see inside my laboratory. You have the real things. So this was far out, and it's still far out. I said, even after 40 years, it's still far out, it still doesn't exist. And in a way it's surprising, because I sat on a committee in '61 discussing this problem, and we learned that you need 1 million joules of light to hit the missile to damage it. And I figured out if a little ruby like this, 1 cubic centimeter, puts out 1 joule of light, then I need 1 cubic meter, which is 1 million cubic centimeters, to produce 1 million joules of light. And a cubic meter of neodymium glass was quite a feasible concept, it looked like. But to control that amount of light energy, you have to be much more sophisticated. You just cannot take just a cubic meter of glass and hope you get 1 million joules out. So there are very deep scientific reasons why it hasn't worked. Well, let's back off from these military dreams and go to some real applications. I might add that the total laser market in the year 2000 amounted to $6 billion US, and that more than 80% was for peaceful and civilian purposes. and less than 20% of the market is now for military purposes. And here you see the first application of a helium-neon laser, which was used to align a tunnel for the subway system of San Francisco, so-called BART system. And this red line from this helium-neon laser onto downtown San Francisco, you see it there, was used to align that subterranean tunnel. Now, all the big pipelines, gas pipelines, oil pipelines, all the verticals and horizontals of the big buildings that go up here in Bangkok use the lasers to align them. So it's very important in the construction industry, although it's scientifically a very straightforward application. Here you see another very widespread application. Can you see these little blobs on there? They have a dimension of about 1 micron by half a micron. And these were produced by focusing a laser, which you can focus as a microscope objective to that smaller size, wavelengths in each direction, of a CD disc material, which was covered by a photoresistive material. And wherever the light focus hit the material, you could then chemically etch these little dips in it. And that is how you can write on a CD disc. And you can put 1 bit of information, 1 if there is light and 0 if there is no light. And so you can write 1 bit of information on a very small area of about 10 to the minus 8 square centimeters, 10 to the minus 4 times 10 to the minus 4. And then you can ask, how many of these spots can I put on a CD disc? And a very simple calculation shows you can put about 10 to the 10th of these bits on a CD. 10 to the 10 bits of information. And now people have gone to a wavelength that is twice as short, frequency of light twice as high, and then you can put 4 times more bits on there. So the high definition CD discs now contain almost 10 to the 11 bits. And that is a lot of information content. That is about equal to the total information content of the Encyclopedia Britannica. And you can write that information on 1 CD disc, and you can read it out with another laser, a little semiconductor laser that is in every CD player to read out where these little bubbles are. So optical storage of information is very important, and lasers play an essential role there. And then we come to the problem of transmission of this information to any place in the world. And that is all done by the remarkable development of optical fiber communication systems. Because the laser can be focused so precisely, you can focus it into an optical fiber. Now, a human hair has a diameter of 30 microns. An optical fiber has a diameter of about 10 microns. So it's much thinner than a human hair. But it has an interesting glass structure. The outer part of the fiber has a lower index of reflection than the center. And that is why the light, by total internal reflection, gets confined to the fiber. It travels along the fiber, and as the fiber bends, the light bends. And that is the idea. And now these fibers can have lengths of up to 10,000 kilometers or more, so they can cross even the Pacific Ocean. Of course, on that long path, there is some loss due to Rayleigh scattering of the light, and you have to amplify it. Now, it used to be that in order to put an amplifier in, they converted the light back to electronics, amplified the electronics, then converted back to light. But even that is not necessary anymore. What they do is they put sections in the fiber that contain erbium ions, a rare earth, but it has an energy level structure rather similar to the chromium in ruby, but different spacings between the energy levels. And they pump that erbium and it acts as a laser in the fiber. So you have fibers, erbium doped fiber amplification, and you can transmit optical signals, pulses between here and the United States, which never have to be converted back to electronics. You just send the light under the Pacific Ocean and it gets amplified here and there, and you can read the signal sent from here in the United States by laser action in the fibers. Okay, let's just see the history of this. The first optical fiber was laid under the streets of Chicago in 1972. And this was between two telephone exchanges in Chicago. And in big cities like that, Chicago, New York, there literally is very little room to lay more cables under the streets. So you take a tiny optical fiber to send a lot of information between telephone exchanges. And then 8 years later, the whole United States was already covered by an optical fiber network connecting all the major cities. And then in 83 or 84, the first transatlantic cable was laid under the ocean, and this is the ship. And here you still, here you still see one of these converters, amplifier stations that converted back to electronics before they could send it on to the next fiber length. And that's not necessary anymore. Now you put just a section in that contains erbium. And this connected the east coast of the United States with France and England. I don't have more recent slides, but let me just read what we have now. Thailand and Southeast Asian countries are connected with Western Europe by a system that has a cable length of 39,000 kilometers and covers 11,000 kilometers underwater. And that cable system has 40 landing points in 34 different countries. And it only contains 2 optical fiber pairs, but each of these can send 20 gigabits per second. So that's 2 times 10 to the 10th bits per second. So they can send the content of an old-fashioned CD in 1 second between here and any of the other countries I mentioned. The largest capacity system, also operating since 1999, since about 5 years, is the so-called flag Atlantic system. It's the fiber link around the globe, that's FLAG stands for. It is a system that cost $1.6 billion US. It took 27 months to lay by 5 cable laying ships. It required 4,000 permits from various governments and participating communication companies. It has 6 fiber pairs, and it uses a sophisticated process which is called wavelength division multiplexing. So each fiber can simultaneously use 40 slightly different optical wavelengths so that it can accommodate 40 channels simultaneously. That's per fiber. And since there are 6 fiber pairs, the total capacity of transmission is 2.4 terabits. per second. The terabit, of course, is 10 to the 12 bits. So it can send the Encyclopedia Britannica in less than 1/10 of a second between the United States and Western Europe. Or it can have the capacity for 200 billion simultaneous telephone conversations. Or if you want to look at movies, it can simultaneously transmit 450 high-definition digital movies. So we really created an overcapacity in optical communication around the globe, and maybe that was part of the trouble, financial trouble of the optical communication systems about 3 years ago. But the physics potentialities have been enormous, have been realized in the last few decades. And this is the initial expenditures. I don't have a more up-to-date slide, but it went up to 10 billion or more for just fiber optic communication. Let's now go back to some other applications of lasers in the industry, metalworking industry, automotive, shipbuilding. This is a picture of a CO2 laser that can really put out a lot of energy. It has 5 kilowatts capacity of light, infrared light. The CO2 laser emits a 10 microwave light in the far infrared. It's a sort of heat wave. And you get 5 kilowatts here, and apparatus exists for 30 kilowatts of continuous power in infrared radiation. And they are used to drill holes in 1-inch steel plates, to weld steel plates of that thickness together, and do all kinds of other things in the metalworking industry. And here you see a laser beam system used for welding of automobile underbody bodies. What is a little more sophisticated and interesting is the working, the hardening of surfaces. If you have an auto-cylinder or an automotive engine, you want the cylinder wall to be very hard so that it doesn't wear out. But what was done in the past to get this hardening is you would cold cool the whole, heat the whole cylinder and then dip it in cold water, so-called quenching, and that would make the metal harden. But of course you didn't only harden the surface, you hardened the whole workpiece, and it could crack. Now here is the laser, there's a rotating mirror. You put a focal point and you go along the whole surface of that cylinder wall very rapidly, and you locally melt the surface with only a very thin layer, and then the light focal point is gone again, and the heat gets dissipated to the inside, so that that little molten surface layer resolidifies and cools very rapidly because it loses its heat immediately to the metal wall under. And so really do just what you want. You harden the surface, but you keep the toughness of the main mechanical part. And clearly, gear of any involved shape can be treated that way. You can make the surface of all these teeth and gears very hard while keeping the toughness of the main body of the metal. And this is drilling of holes in a jet engine blade. Jet engines use titanium blades, and the performance of a jet engine is limited by that very high temperature that the tips of these blades get as they whirl around in the gas stream. And in order to prevent the tips from melting, being able to operate at a slightly higher speed of the jet engine, you drill additional cooling channels. And that's what is done here there is a CO2 laser that drills a little cooling channels near the tip of these jet engine blades, and it improved the performance of the jet engines by maybe 1 or 2%, which is very important from an economic point of view. Now we go from the high power back to low power, and this is extremely low power machining. And what is machined here is a human hair. And you can drill a hole in a human hair by using UV excimer laser codes. And you see, totally useless, of course, but to demonstrate the precision and the control one can have with a laser beam in machining body parts, literally living body parts. Since the laser beam can be focused to about 1 micron, you should realize that the sharpest surgical knife, scalpel, has a width of 10 microns. So a laser beam acts like a much sharper knife, and it's also more easily controlled because you don't open it in your hand and shake it. You have a mirror that is mechanically operated, and you can see exactly where you want the radiation to go. But not only that, if you cut through a blood vessel, the knife makes a bloody mess because the blood flows out from both sides of the artery of the vein you've cut. Not so with a laser cut, because the laser cuts by heating the blood, and the two ends get automatically cauterized. So laser surgery is more precise and much cleaner than surgery is that nice. You have to be careful with lasers. You have, if you look in an ordinary light bulb, you get an image of the light bulb on your retina, that's fine. You see the light bulb. You don't look in laser beams, not even low power ones, because here the light gets concentrated to about a few microns. And even although the laser is not very powerful, it may work. You see, the laser beam does nothing as it goes through the transparent lens and body of your eyeball, but right here are the blood vessels of the retina. That's where the laser light gets absorbed, and that's where it can do damage. Now, so if you have powerful lasers, you have to use focus and laser wavelengths from reaching the retina. But doctors use it to make damage on purpose. What happened here? One slide doesn't work, never mind. It showed a patient lying in a doctor's office, not in a hospital, with an argon ion laser, and the doctor looks where the laser gets focused. And it gets focused not in the point of vision, but it gets focused at this series of points here, and that's it. And what are those white spots? That is scar tissue, because the argon ion laser beam. This is the forehead of an 80-year-old man who was born with a port wine stain. And this used to be inoperable, and people had to live with those port wine stains as long as they lived. But this 80-year-old gentleman got laser treatment, and he got a nice forehead skin. And here is the physics behind that. The doctors used pulse lasers, and you should know that the port wine stain is caused by that the skin has little areas everywhere with too many blood vessels. That's why the skin looks red. But in between are pieces of normal skin. And now you take a laser, or argon ion laser or what, and you get more absorption in the red spots than in the white spots, because simply more light gets absorbed by the red skin than by the white skin. And then you dose it so that the skin that's too red, the temperature rises. You don't want it to boil, and you don't want to boil a person, but you want to do the same as you do with an egg, cooking it. You coagulate the protein, you denature the protein, and that if you reach the temperature between 75 and 100 degrees centigrade, you destroy the cells in that area of the skin. And you dose it carefully so that you only kill the two red parts to keep the parts that are white. And then they grow together, and that is how you get rid of the port on the skin. Of course, surgeons can be more sophisticated than that. They can send laser light into an optical fiber, and they can thread that optical fiber to your artery right into your heart chamber. This has been done. And then they drilled holes in the heart wall, but not completely through. You don't want to get a leaking heart, but halfway through. And then the heart felt damaged and started to grow new blood vessels to control the damage. But that's just what they wanted, because this heart didn't get enough oxygen from the existing blood vessels. But if it grows additional new blood vessels after this procedure, the heart muscle revives better. Well, so you see, these are all examples of very peaceful and beneficial applications. And I think the two most important ones for individuals are these applications in medicine and surgery, but also the idea of global communication, that you can use your cell phone and call anywhere in the world by your optical fibers. You can receive emails from far away, and you can look up the World Wide Web, all due to optical fiber communication. Now, there are military applications, not the Star Wars idea of anti-missile defense. That is still far into the future and may never happen. But what does happen is that every tank has a laser rangefinder. It doesn't matter whether it's an Iraqi tank or a US tank or a Thai tank, they have laser rangefinders. When you send out a pulse of light, and you look at the light reflecting back and see how long it takes, that gets you the distance. Also, very important is the concept of target designators. That you shine a laser beam of a very particular color onto a target, and then a pilot or a smart bomb homes in on that color. It's the appropriate filters. And so it knows where to hit. And the first example was that during the Vietnam War, where they had big trouble hitting a bridge. Instead, they hit 10 times around the little villages. Then they used a laser target designator, and the next one really the bridge right away. So perhaps not all military applications are terrible, but they may even be somewhat beneficial. And let us end then with the main conclusion of this talk. And that this slide shows you the development of the laser market, which is the red line, which is dotted from the year 1982 on, because this slide is already that old. And it was conjectured that the laser sales would increase like that. Why? Because they said the behavior is very similar to the blue line, which was computer sales, semiconductor, electronics development. But that curve started 17 years earlier. And so the lasers followed the computer market with a delay of 17 years. And also, of course, the discovery of the transistor preceded by about 15 years, almost 17 years, the laser discovery. So, but then the economic development between these two big fields was very similar. And the prediction was that in the year 2004, we would have to look at the computer market 17 years earlier, which was 1986. And it's remarkable how well this analogy has held up. And as I said, the present market, it was 6 billion, it's now about 10 billion. That fits pretty well with this curve. But remember that 80% of these amounts is for civilian purposes, less than 20% for the military. Thank you.
For your very thought-provoking lecture, Professor Bloembergen. Now, I would like to invite some questions from the audience, if I may. And the question may be put in English or Thai. I shall try to translate the Thai question as much as possible. So, is there any question from the audience? มีคำถามหรืออะไรนะครับเกี่ยวข้องกับเลเซอร์เกี่ยวข้องกับแอปพลิเคชันหรือ future development มีไหมครับหรือเขียนขึ้นมาก็ได้นะฮะ you may write itเชิญครับ
Carbon dioxide laser, how to work? Can you explain it again? For surface hardening.
Explain what?
Carbon dioxide laser for surface hardening.
Yes, you show one example of how you could harden the surface of the metal using carbon dioxide laser. She would like you to explain it again. I think she missed some points.
Well, you focus the laser beam on the surface of the metal, and it immediately melts. But the laser spot is moving around very fast, so you melted only a very tiny layer for a very small time. And once that is locally melted, it loses its heat and resolidifies very rapidly because of heat conduction from that little molten bubble on the surface to the interior. So you don't heat up the big cylinder wall, you only heat up the surface, and that surface also gets cooled very rapidly because the heat conducts back into the substrate.
พอเข้าใจนะครับ Why they reformulating the question? I have one question. Perhaps in your work, you once have been working with the picosecond and femtosecond pulse from laser interaction. What is the potential of the femtosecond pulse X-ray or laser now that you can see, for example, in biophysics or in condensed matter physics?
Well, you're quite right that we have now laser pulses that are on the order of femtoseconds. The shortest laser pulses are a few femtoseconds. What can you do with these short pulses? You can do investigations of time resolved spectroscopy on that time scale. And if you take two atoms that are going a chemical reaction, the duration of the collision is on the order of 10 femtoseconds, 10 to 100 femtoseconds. And with short length pulses, you can do spectroscopy as these two molecules hit each other's electron orbitals. And so you get a very precise idea how a chemical reaction proceeds. And a lot of this work was done for many chemical reactions by Professor Ahmed Zouweil at Caltech, and he got the Nobel Prize for Chemistry in 1999 for femtosecond time-resolved chemistry. That is one example. You also have examples in solid-state physics and even in biology. People have the first step in the vision process is a change of a molecule in your retina called 11-cis retinol to an isomorphic form which is all trans retinol. The shape of the molecule can change, although its chemical composition is not changed. And that is the first step in the vision process. And people have analyzed that, and it takes less than 100 femtoseconds to deform that molecule from the 11-cis to the all trans isomer. So people in biochemistry also use the short pulses. The real push there is you cannot go to sub-femtosecond pulses because a femtosecond is the duration of one light period. If you want to go to shorter pulses, you have to use higher frequencies. And that is still a wide open and a difficult field. And people start to try to get X-ray pulses. That would be less than a femtosecond pulse ratio. Very little is known.
Professor พูดถึง femtosecond. This is just for the benefits of the young audience. I just briefly translate what you just said. คือผมถาม Professor เกี่ยวกับว่า pulse ของเลเซอร์ที่มีขนาด femtosecond นั่นก็คือ10กำลังลบ15วินาทีนะครับ femtosecond นะว่าขณะนี้เนี่ยมันมีการใช้งานหรือการศึกษาอย่างไรบ้างนะครับโปรเฟสเซอร์ก็บอกว่าไอ้ขนาดของห่วงเวลา10กำลังลบ15วินาทีเนี่ยมันเป็นห่วงเวลาของการยกตัวอย่างการเกิด reaction ต่างๆของอย่าง chemical reaction เนี่ยมันจะเกิดอยู่ในห่วงเวลานะฮะประมาณ10 ถึง 100 femtosecond ครับดังนั้นเนี่ยเราสามารถศึกษาได้เลยว่าโดยใช้เทคนิคที่เรียกว่า time dissolve นั่นก็คือว่าจับในห่วงเวลานั้นนะยิง pulse นี้เข้าไปนะล็อกในห่วงเวลานั้นเหมือนกับเราถ่ายรูปแล้วฟรีซมันในห่วงเวลาในช่วงfemtosecondนั้นเนี่ยเราก็จะสามารถศึกษาได้ว่าปฏิกิริยาที่เกิดขึ้นนั้นมันเป็นอย่างไรนะซึ่งทั้งในทางเคมีในทาง solid state physics หรือแม้กระทั่งในฟังก์ชันของเมมเบรนของเซลล์ต่างๆนะครับอันนี้เป็นฟิลที่คนที่ทำทางด้านนี้เนี่ยได้รับรางวัลโนเบลไพรส์ไปเมื่อปี1999ครับผมก็ขอเพิ่มเติมไปด้วยว่าที่มหาวิทยาลัยเชียงใหม่เรานั้นเนี่ยภายในปีนี้เราคาดว่าเราจะสามารถยิงอิเล็กตรอนซึ่งมีห่วงอยู่ในเรือนของ50 ถึง 100 femtosecond ได้นะครับดังนั้นคิดว่าถ้าน้องๆที่หลานๆสินะคนไหนที่สนใจทางฟิสิกส์ซึ่งมีฟิสิกส์มากมายเหลือเกินนั้นเนี่ยในทางนี้ก็ลองคิดดูว่าคิดถึงฟิสิกส์ที่มหาวิทยาลัยเชียงใหม่นะครับ yes please
From Chiang we all know what MRI is. What is nuclear MR?
MRI uses a nuclear magnetic resonance. They just left the word nuclear out.
I thought there's something new.
No, the nuclear magnetic resonance is about as old as electromagnetic resonance. And it was originally known as NMR, nuclear magnetic resonance. But the medical people thought that some of the patients might be very worried if they use the nuclear magnetic resonance procedure. But that's what they use.
Chiang.
Sukum, former professor of faculty of engineering at Chiang University. I'm very glad to have a chance to listen to your talk. It's very interesting. I think I'm probably only the engineer in this audience. Well, very interesting. You have shown us the applications of the laser technology in both war and peace. And you have mentioned that 80% of the application have been used in, peaceful. Only 20, especially in Iraq war. You have seen that application a lot from CNN. Would you forecast in the future the trends of application in war and peace, especially in my field of profession, engineering? Would you forecast that?
Well, I think a lot of more progress will be made in the medical and surgical field in the next decade. Clearly, more and more medical and surgical procedures will start using laser beams. It can be improved by. I think in the field of optics communication, probably I don't foresee that much further improvement. We have such an enormous development there. What would be very interesting is to go to X-ray lasers and even shorter pulses, and then you could make X-ray holography, and you could see how the electric wave patterns move inside molecules and materials. Clearly, a lot to be done in connection with nanoscience. There is a big engineering tendency to make nanostructures, and there laser processes also play an important role. And that may lead to new technology of quantum computing, which would be clearly based on a coherent state between lasers and atoms.
Well, first of all, I would like to congratulate you on your success in delivering such a thought-provoking lecture. I have a very straightforward question to ask you on behalf of these young students. It seems to us that most of the Nobel successes have derived from advanced technology in instrumentation or the use of sophisticated instruments. But for Thailand, which is a developing country, would there be any chance for us to win any Nobel Prize in the branch of science? Would you give us any light, please? Thank you.
Well, there is a chance. The main thing is to ask an interesting question and then work very hard to try to get an answer. Now, clearly, a lot of advance and a lot of Nobel Prizes have gone to theory and didn't require much in the way of equipment. Maybe access to a computer, but you will have that here in Thailand too. So from a purely theoretical point of view, I don't see any difficulty there.
How are we going to win the Nobel Prize? Top student will talk to study science.
Well, forget about the Nobel Prize. The important thing is that you get some students interested in asking a question that is of interest, not only to the student in particular, and then he wants to find an answer. You have to work long and hard hours to think about it, but eventually you get the satisfaction that you find out an answer to a problem that maybe new and nobody else had thought about. And I was often asked the same question in other Asian countries, including Japan and China. And although they have quite good technological basis, they also wondered how do you get a Nobel Prize? There are two requirements. One is that you have a little bit of luck, and second, that you live long enough. But the point is this, that there are many roads that lead to Stockholm, and each Nobel Prize had its own individual road. But there are, of course, a larger number of roads that lead elsewhere, but that's not necessarily bad, you know. The main problem is that you get an interest in a science problem, and that you stick to it until you have found an answer. And then, of course, there's always should be the possibility for promising students to go abroad for 1 or 2 years.
In Thailand, it is pretty sad. We have quite a few number of students who are Olympic medals, academic Olympic medals, but finally they often study medicine and engineering.
Well, the same problem happens in the United States. You know, the best students go into medicine and in law, and they can earn more money, and so staying in silence. Coming to the United States, 40% of our science students are foreign.
Professor บอกว่าวิธีที่จะได้รับรางวัลโนเบลไพรส์นั้นไม่ยากนะครับมีชาร์จอยู่เสมอตามกฎของกฎทางเมคานิกส์นะฮะมีชาร์จอยู่เสมอถ้าหากว่าขอให้เราได้ถามคำถามที่ถูกต้องแล้วก็ work hard อย่างที่เราเคยพูดกันทุกครั้งว่าเราต้อง work hard นะครับดังนั้นอย่างไรก็ตามในทางทฤษฎีโปรเฟสเซอร์บอกว่าเราก็มีโอกาสเท่ากับที่อื่นเขานะครับถ้าเราสนใจจริงๆจังๆนะครับ Is there any other question มีคำถามอีกไหมครับ I have the last question if I may please going back to 1981 1981, I hope you still remember an occasion when you went up the stage to receive the prize from the king. Just before you took the prize, what was in your mind at that time? What were you thinking about?
Well, I was hoping that I wouldn't do a misstep or drop the medal. Just at that time, you know, the physics people, by tradition, get the first prize, and then among the three physicists it went alphabetically, so I was the first one to stand up on the podium, and I was afraid that I would do something wrong.
Thank you very much. Yes. If there is no more question, may I now invite Dr. Chandan Anduman Nashathon, Vice President of Chiang Mai University, to present a souvenir to Professor Bloembergen.
No, that's just my Stockholm.
Except we need a bottle of wine.
Oh, that's perfect. That's perfect. Thank you.
And now, you know, in Thailand, the ceremony is long, as you know. Sometimes as long as the lecture. Now, I would like to invite Professor Bulatsa Sinthorntham, the Dean of the Faculty of Science, to say a few words of appreciation about on behalf of us.
Professor Nicolaas Bloembergen, Vice President of the Chiang Mai University, Dr. Chandan Anduman Nashathon, academic colleagues, distinguished guests, ladies and gentlemen, I would like to express our sincere thanks and appreciation on behalf of the Faculty of Science at Chiang Mai University to Professor Nicolaas Bloembergen, the Nobel laureate in physics, for his remarkable lecture on science and global communication based on optical science and technology, especially about the application of the laser technology to very interesting. The visit of the Nobel laureate to our faculty has to be indeed a very special occasion, and we are in debt not only Professor Bloembergen, but also to the International Peace Foundation for making today's event possible. Today's special occasion is considered to be very much part of our celebration for the 40th anniversary of the Chiang Mai University in this year. Even though it has been a very brief period, we hope that you will enjoy your visit to Chiang Mai and also the Chiang Mai University. And I hope to see your visit to Thailand and Chiang Mai again very soon. It has been a pleasure and a privilege for us to host this third of the Nobel Prize laureate lecture. Thank you very much.
I believe the Dean has a small souvenir to give to Professor Bloembergen as a token of our sincere appreciation for your lecture. Now, I would like to ask us to give Professor Bloembergen a big hand for our appreciation of this. The the student would like to take some photograph with you, may they? Okay. เชิญเลยครับหลังจากนี้นะครับจะมีทีเบรกซึ่งขอเชิญท่านร่วมในการสนทนาและรับประทานน้ำชากับโปรเฟสเซอร์เลยนะครับ
เด็กๆกลุ่มนี้อีกกลุ่มจะถ่ายเดี๋ยวถ่ายให้ด้วยไม่ได้โรงเรียนลูกตัวเองถ่ายก็ได้
เอามันไหมครับ
นี่ไง
เขาอยากถ่ายด้วย
อ่ะไม่พี่ไม่ถ่ายแต่จะให้เราถ่ายให้ตั้งอันนี้เลยเหรอ
อันนี้มันพี่เขาฝากผมถ่ายไว้ครับเบรกก็จะมองไม่ได้
Now we have a coffee break that we could talk more with Professor if we would like to know more something.
แกถ้าจะทนไม่ได้เมื่อไหร่สักคนจะถามสักทีอันนี้แกเตรียมคำถามมาให้เราแล้วเหรอแล้วถามก่อนนะเราค่ะไม่ได้ตอบว่า